Okay, in today's lecture, I'm going to introduce some numerical tricks or methods to numerically calculate optimization process. Maybe we can start with Google spreadsheet. So let me go to this place and then create a Google spreadsheet. Okay. So this is the 0325 optimization example. Okay. So it's okay if you do not have the link for now. You can listen to my lecture. And meanwhile, when I show you some programming tricks, if you didn't learn that command, you can keep a note. Okay? So if I want to solve an optimization problem in a spreadsheet like this, definitely I need to figure out how to input my numbers to the spreadsheet. So whenever you are working in a Google spreadsheet, if you don't know how to program, I'm not going to talk about something very high tech, such as create your own function. That's I think that's too much. I'm just going to use the simple ones. But definitely you need a list of functions so you know what you can do in Google. And here you can say help, and you can see a function list. So click this. It's a menu for all the functions in Google Sheets. Okay. So for example, if you want to do dot product over here is going to be matrix multiplication. So MMULT, matrix multiply. So if you don't know Google Sheets can do this, then you are basically doing calculation element by element. That would be very inconvenient. So for example, I have several numbers like 1, 2, 3, and here I have 2, 3, and 4. I want imagine if those two are two vectors with random numbers. I want to do a dot product of them. What can you do? You can say M multiply. So that's basically multiplication of two vectors. But when you do dot product, the first vector has to be horizontal vector. The second one has to be a vertical vector. Right now, the way you arrange the numbers are in a vertical direction. So you need to do a transpose of your first vector. So over here, what you can do is transpose. So transpose in here is transpose. Bracket, and just do this. Just select from A1 to A3. And then comma. Now you select B1 to B3. Close this. Okay, so M multiply bracket transpose bracket A1 to A3, representing the vertical vector. And the second column is B1 to B3. Once you do that, this is basically the dot product. This one is your dot product. Okay, so in Google Sheets, you can write a lot of functions like this to help you to do calculation. When you program a lot of different things, then you could just change numbers and you get the solution, right? Okay, so this is just a way for me to introduce you to the world of Google Sheets. And if you need to know any function, you can find from here. You can even type in some keywords. For example, text. You want to know things about text. So there are a bunch of functions regarding to text. And you can click Learn More to see more details about a specific function. They inform you how you can use the function and the syntax, what does each input represent, and also some related functions. And the best thing about this is that there's an example at the bottom. Okay, so this is like a system created example, and usually they provided multiple cases. Okay, so you can read, but let me see. Okay, so the example is right here. Like if you type in like this, you can get a result like what, and usually there's a reason, and you need to learn about the function. And here are like different ways of programming, and this example tells you the results. You really need to spend time on getting familiar with the functions, then you can make good use of it. Okay? Now, let's get back to what we want to do. So to work on a optimization problem in a Google Sheet, I think the most important thing is that you need to be able to describe your function, right? So let's see if we can do sine and cosine. I think we can. Math. So we have arc cosine, absolute. We have all kinds of math functions. So actually, you can describe your function based on the tools right here. So let's say I want to work on a how about 4-dimensional problem? Okay, so let's work on a 4D Do I need to work on a polynomial problem? Maybe not. Just 4D minimization problem. Okay, so 4-dimensional. Let's just define how large our design space is. So now 4 variables. And I'm going to say here is my initial guess. Okay, I'm gonna use the following 4 elements to represent my initial guess. So here, let me change the color so later on I can easily find them. Okay, my initial guess. So right now I can just randomly put some numbers in there, just for me to use later on. And you really need a way to plug in those numbers and then get some response from a function. So maybe I will treat this as the main function. Okay, so I would like to use another sheet to formulate my function. So later on, whenever I use some information from the other sheet, then I could easily plug in the number and get a response. So maybe over here I create another sheet by clicking the plus sign right here. And over here, let me change the name. This is going to be my function. Or maybe just func. Just make it short. Okay, so later on, whenever how do I plug in and then get numbers? Let me think about it. if you want to plug in a number, because that would be the key for this code. If you want to plug in and do it, what would be the best way? Actually, not easy. Let me remind myself how and check how did I do it in the past. I did it once in the past. I just want to remind myself what I did. Maybe here. How about this one? No. This is not the way. So maybe I need to. Maybe there's not a good way. So I guess the easier way to do it is to work on polynomial for now. Polynomial, I can figure out an easy way. How about if I want to specify the function manually? Okay, let's work on a polynomial first. For the polynomial minimization problem. So my function for now, my function is a polynomial function. So what does that mean? My function form is like this. I will be working on maybe 4D is too much. Maybe just 3D, 3-dimensional. Okay, so my function form will be x1, but quadratic, polynomial, quadratic, which means second order, quadratic polynomial, okay? Because if I work on a 4D problem, it's going to be having a lot of coefficients. It's taking a lot of time. So here I will be plugging in the coefficient for x1 squared, and then x2 squared, x3 squared, 3D, right? So I have x1 and x2, x1, x2 and x3 and x1. Now I have the 1D terms, x1, x2 and x3, and I should have a constant. So I will be giving out several numbers at the bottom which represent the coefficients for each term. Okay, so for example, I have 2 x1 squared, 3 x2 squared, 4 x3 squared, and maybe I give some numbers here randomly. Okay. Just random numbers. Okay. So with these numbers, I could describe what my second ordered 3-dimensional polynomial looks like. And I need to know how to plug in and then get numbers, right? So the way to plug in, basically, for example, here an example of plugging in initial guess to the function. Okay, an example. So here what you can do is you can write a code. So the code will be basically x1 squared, like this, plus x2 squared plus x3 squared, and then it's a 3D problem, so I don't I don't need this one. Only three. And these are my coefficients, okay? Coefficients. So I can say the first one square. Oh, by the way, I need to say that this is the first coefficient. Coefficient is here. Sorry. The first coefficient multiply, and this one square, and then plus this one times this one square plus this one times this one square. You can continue to do that. Then you have a one element that is being programmed to evaluate the plugging in. Okay, and maybe you can later on you can make good use of that description. So you can plug in numbers to a function and get values. And then later on you can keep on programming this to you can type in the equations for Newton's method. So you can keep on building those. Then this could be a optimization process sheet. Okay, so I'm trying to see if I can make it more efficient. Okay, so actually I figure out a better way to. From here you can see you can actually type in the equation, but that takes too long to type. And whenever you need to plug in, you need to type in those mathematical description again. That takes too much time. So I suggest you to use dot product. So how do we use dot product to do it? What you can do is you can make this one x1 squared. Okay, so this one is what? Hold on. I should say. So I should highlight. Yellow is the coefficients. Okay, yellow means the coefficients. Okay, but here I'm going to do the x1 square operations. So here the following I'm going to do, and then I'm going to use green color. Green means evaluation of each term in polynomial. Okay, let me do that. So the following I'm going to use green. Okay, here I'm gonna say I know the first one should be x1 squared, right? And this is my x1. So I'm gonna say this guy squared. Okay? And second one, I should evaluate x2 squared. So here is x2 and square. Okay? And this one is x3 is this one and square. Okay? Now this one should be x1 multiply x2. So I'm not truly typing the entire equation. I'm just typing, I only need to type in this element times the other element. Okay, that will be a little easier. And then this one is x2 times x3. Okay, this one is x3 times x1. Just be patient and continue to do it. Now this one should be x1, and this one should be x2. and this one will be your x3. And you don't need a last one because the last one, it's a coefficient. So what do you do for coefficient? You just type in 1. Here is truly 1, okay? But you see a lot of 1s here. How come they are all 1s? Because my initial guess is 1, 1, 1. What if my initial guess is 10, 20, and -5? So you will see each terms will be updated automatically, right? And of course, the coefficient term still keeps a constant value 1. Now, the beauty of this is that you can use dot product to evaluate the function value. So now I'm gonna use dot product to get the function value. Okay, so how do I do it? I use what I told you, matrix multiply. So when you have two, if I can do this 2 multiply 100 plus 3 times 400 plus 4 times 25 and continue to do that until the last term, sum them together. That's the function value, right? Because the yellows are the coefficient for my function. 2 times x1 squared plus 3 times x2 squared and so on. And what I want to plug in is in the green. So I can use the yellow vector and multiply my blue vector. I get the function value. So over here, I will say m multiply. But for m multiply, I need a horizontal vector multiply a vertical one. So let me choose this one as my horizontal one. And for the green one, I need to transpose it. So transpose. And transpose, you will get this one. Okay? So at the end, this is your function value. Okay? This is your function value. If I change it, if I change to 0, 0, 0, since this function has a constant of 6, so if I use 0, 0, 0 to plug in, I should get a function value of 6. So now you know, if I change values here, my function value changes. Okay, so it's a way to plug in numbers without typing the entire function and make good use of the dot product. Okay. So now at least we can plug in. So the next is, can we use whatever we have here to solve optimization problem? Okay. Let me see what we need to do next, because we need to do a lot of plug-in later on. This position is gonna change. Okay. So let me. I'm not sure if it's okay. Okay. So let me make a little change just for us to let me see if that works. Let me think about it. I have those. How I can. I just want to make it efficient, and so later on we can quickly solve the optimization problems. Okay. So maybe I will do a copy down and then. Okay. In order to show what I would like to do, maybe I need to move the whole thing to the right hand side. So later on I can directly just copy down the process. Is it a good way? Okay. But I feel like that's a stupid way to do it. Maybe you spend a lot of time arranging the elements, but later on you still get similar things. So I feel like that would be wasting our time. Okay, so let me just show you. So here I only show you the and multiply. I didn't show you much. How can I do a better job? I didn't show you much. I'm sorry. I want this whole thing to be very automated, but because for Newton's method, this only converge in 2 iterations. So we will spend a lot of time programming this, and then you get solution in 2 iterations. So that would be quite stupid. Yeah. So maybe Google Sheets will be better for use later on when you learn something called linear programming. So here I did linear programming, but this is not the main focus for today. Like later on for linear programming, Google Sheets can do a better job. Okay, so I'm gonna introduce Google Sheets for linear programming later on. I don't think Newton's method is very suitable for Google Sheets. It's doable, but you spend too much time on programming. So I'm sorry. Let me move on to Matlab. Sorry about wasting a little bit of time. You only learn one thing, matrix multiply. Okay. Okay, so for Matlab, it's more flexible because you basically program everything based on your will, right? You can program anything. So let me show you how to start from scratch. And if you do not have Matlab, our department has Matlab. Okay. I need to turn off something. I need to turn off this. Sorry, because that software is conflicting with Matlab, so it's taking a little time. Maybe I restart. Okay. So I'm gonna start from a script. Okay. So create a new script. What you can do right now is to initiate your programming. Usually what I do in the first line, I will clear CLC and close all. So what does those mean? Clear means clearing your memory in the workspace. So in Matlab, you have a workspace. You can have a lot of variables. For example, x1 equals to 1, x2 equals to 2, something like that. So in your workspace, it will memorize those variables and the values that you get. But to start a new code, what I usually do is to clear the workspace, start from scratch. And what does CLC mean? CLC means I want to clear the command window. So if I say CLC here, the command window become clean. Okay. And what is close all? If I have a figure, and if I don't close the figures, my program will keep on creating new figures. Then you will have a lot of figures. So if you say close all, you will close all the figures. Okay, so this is the way to initiate what I usually do. Okay, and in optimization problem, you need to define the math functions. So over here, usually you could use 2 percentage sign to break into highlighted sections so that it's easier for you to read. So over here, I'm gonna initialize the problem, and later on, I'm gonna do your iteration loop. Okay. So in the initialization part, you're going to define your variables. So what you can do, maybe you can say x, and you can start with some random number, maybe 0, 5, 5, 4. Let's try a 4D problem. No matter how many variables, that's fine. Okay? So if you are not familiar with Matlab, 1, 2, 3, like this, is the same as 1, 2, 3. Okay? But if you say 1, how do you call this? I don't know how it's called. Chinese 分号, but what's the English of it? Semicolon. Okay. If you use 1 semicolon, 2 semicolon, and 3, semicolon will, it's like change the line in a matrix. So you are forcing this to be arranged in a vertical way. So at the end, you have 1, 2, 3 vertically. Okay? So you need to know about how to, what does it mean in Matlab. Okay? So this is going to be my initial guess. Okay? So percentage, whatever behind percentage will be the comments. It has no function inside the program, but it's helping you to read. And later on, you need a iteration number. So in our lecture, we usually use k, right? So you can start from 1, because usually in our lecture we use k equals to starting from 0, but in C++, the index for the first element is 0, so which is the same as our math. But in Matlab, the index for your first element is 1. So you can say x bracket 1. Oh, I didn't define x. You can say x bracket 1. That means the first element of x bracket 3, the third element of x. But if you cannot say x bracket 0, because there's no number 0 in the Matlab. So that's why we start from k equals to 1. Because later on I'm gonna say x bracket some number. I cannot start from 0. Okay? Then you need your function. There are multiple ways for you to plug in a function. So let me say f equals to what you can do right here. There are 2 ways. So let me show you the first way. You can define your function you can treat your function as a description. So you can say sine x1 plus cosine x2, for example. You can do that. So if you use the, how do you call this? I forget, apostrophe. But how about the only one? How do you call that? This, what's the name of it? Nobody knows. Okay. Chinese is 引号, is it? Okay, anyway, with this, only one dot in the uppercase. Whatever inside this, that's a string. This is a string, and you basically this is like a character. So you are just keeping your function as a character. So how do you plug in? If you say substitute, SUBS is substituting, and then you can type in your function right here, and it's like a replacing. You are basically replacing x1 by something else. So here text x1, and you are replacing it by a true value, for example 2. I'm not sure what will happen, because in different versions you cannot do it because it's not symbolic. Okay, so maybe I should do symbolic. No, that's a different way. Okay, let me try this. String to symbolic. Okay, then you can do it. Okay, so what's happening in different versions of Matlab? The functionality of Matlab is a little different. So in my version, it doesn't allow me to substitute, to replace the x1 by 2. You can, but it's a different function. So in order to make it work, I need to convert string into symbolic. So symbolic is a very unique way of variable type in Matlab. Symbolic means 代数 in Chinese. So you can plug in. Okay? So in order to convert that, you need to say string to sim. So string to sim means character or string converted to symbolic. So see, I already successfully tested right here. So what do I get at the answer? It's a sine bracket number 2 plus cosine, but x2. x2 now become a symbolic description of a variable. Okay? So, but I need to plug in 2 numbers. So what you can do here is, let me test it. And I think this will work. Just to test. Yes. So if you hold on. Yeah. If you want to plug in multiple numbers at the same time, you can right here try it in this way. So let me rewind and show you the difference. Let me show you two different kinds of way to describe it. Okay, so the first one, plug in the function, only plug in x1. But the second one, plug in both x1 and x2. But in the second syntax, I need to describe what to plug in, right? I basically you replace the value of 2, you replace the string of x1 by the value of 2. You replace it. Right now, over here, you are trying to replace two different things. But those two different things are in the format of character. In order to put two characters together, let me try a different kind of bracket, just to make sure. Because sometimes it works, sometimes not. Okay, see, this is way different. So definitely you need to do what I did. That's the only way to make it work. So it's very different. So you need to use the this kind of bracket. I don't know the English as well. What kind of bracket is it? Okay, it's a very long word, English word. You know how does it called in the Chinese? So this is the small bracket, medium bracket, and the large bracket. There's a 小括号, 中括号, and 大括号. So easy. But, in English, they are different. They're named differently. So I'm going to name this the big bracket. So that's a big one. So what does the big one represent? The big one is a container that keeps different kinds of elements. It's called the cell. So if I use x small bracket number of 2, this is the index for this variable, for the variable. Okay, so this is like what's the position inside the matrix. Okay, so this 2 is like the second one in this variable. Okay, but when you describe a vector, if you say it's a vector like 2, 3, and 1, here you're going to use the medium bracket for Chinese. Sorry. So that's the only way to describe what's inside. So this is the bracket for arrays. Okay, to cover what's inside. But in another kind of way is that so like this one, this is your x small bracket 2. This is your x small bracket 3. Okay? But what if you want to put different kinds of things together in Matlab? You can say x equals to 1, and here is a string. For example, 8. Okay? Okay? But here you are using like a big bracket, because this kind of variable is called cell. And cell can keep many different kinds of variables. Okay? So let me show you. X, let me clear the memory. X equals to big bracket 1 and 2. So see, X could be a cell array. So the first one is a number, second one could be a string. Okay? And string, if you have two strings and you want to put them together, because when a string is a group of characters, now you have two collections of characters, each one represent a set of string. But you want them to be placed together and then you want to use it. The best way to put them together is to use a cell. So it's like you have a cell. The first element inside the cell is your first set of string, which is x and 1. The second room of that cell keeps a string, which is x and 2. That's why I'm using this way. So with this way, you can tell subs that I'm going to replace something here. I'm going to replace this one. The first one is this x1, and the second one is x2. By what? By the first value 2 and the second value 3. So by one line, I can quickly plug in a number into a function. Okay? So this is converting. This is converting string to symbolic and plug in multiple numbers at the same time. Okay? How about the other way? If I say function 2 is like this. I'm not sure if that works. Hold on. No. Incorrect. So yep. Okay. So this is another way to define a function. Okay. So what's going on over here? If you use at right here and describe what's variable inside what's going on here, then this is a way to tell Matlab this is a function. So it's called a function handle. It's called a function handle. Okay? So you can say y is it's gonna be the function inside the description behind it, and you can then say y1 squared plus y2, for example, like that. And you can name this as a function f. So later on, when you specify f and you plug in a vector, because you need to have two values, you plug in 1 and 2. So what does this function do? What it does is that it will plug in a vector to here, and the first element gets into here will be plugging in into the y1, and the second element will go through this handle and then plug it in over here, and it will evaluate the value what's inside the bracket and output the result to that. Okay, and the way to plug it is just to type in this. When you type in this, it gives you the number directly. So the good way of this kind of programming is that it's clean. You don't need to type in something like this. It's very wording, and then sometimes you have bugs. But in this way, it's very clean. Okay, so it's really up to you. Okay, it's really up to you. But the problem is, usually when we have a program, our function form usually needs to be manually provided. So if I manually provided this, how can I automatically convert this into this line? Because you don't want this line to be manually updated, then you are basically updating a lot of things by yourself. You want this to be automatically updated. So let me see what you can do. You want this to be a string, because a math function could be in many kinds of formats. So if it's a string, that's easier. And the good thing about this way is that you could just say f something, then you get the value. So in order to take advantage of both, let me see if I can do that. I'm not sure. So maybe another way is, say, func3, and here I'm gonna use this, and then I'm gonna say func4 equals to I'm not sure if it works. It works. So it kind of combines the advantage of both. Okay, let me confirm if it's correct. Yes. Okay, so if you program in this way, then it has the advantage of both. In the first kind, you have the advantage of telling the computer what your function looks like by typing the text. But to plug in, it's very long. The second way, you can tell the computer, okay, this is your function. But in the future, when you update your function, you need to go to the line and then retype. What if you have 100 functions? You are basically updating 100 lines. Okay? But in this way, you can define those functions somewhere by a string. And in this line, when you defining the function in Matlab, converting it into a function, you can use this way. So what's inside right here is evaluating these strings. So when you evaluate a long string, it will basically initiate a kind of a string converter. So it will try to convert it into what you wrote here, and then evaluate this into numbers. Okay, so that will be a good way for you to put them together. Okay? So I introduce 3 different ways to plug in. Okay? So this is defining functions by this kind of way. Okay? And here is combining the advantage of above 2 methods. Okay, so today maybe we can try to use this nice way. Okay? So these are just for you to know. So over here I should say just for you to learn more about Matlab. Okay? But over here I'm going to get back to optimization. So over here, I still need to define my function. So since I already use func2, func3, func4, I'm not going to use those names anymore. I'm gonna use f. So here my f, I will be doing, for example, x1 square plus x2 square plus 10 times x3 square plus 6 times x4 square. For example, minus 20 x1 plus 15 x2 plus 6 x3. I'm keeping away the coupling terms, and then plus maybe 7. Okay, so I describe my function in a long string. This is my function, and later on when I need to plug in, I'm going to use the trick right here. Okay, I will use that trick to plug in. Now, what's next? To initiate, I need derivative. So let me see if I can derive this. diff fx1. No, I cannot. So I need to string to symbolic. Yeah. So the disadvantage of using this way is that you cannot do derivative. But if it's symbolic, you can do derivative. So the good way of symbolic right here. Good thing about symbolic is that you can do derivative. Okay, you can do derivative. Okay, let me show you how to do derivative. You can say diff and string to symbolic func, and you can do derivative with respect to some x, for example x2. Okay, so if we test this part of the code again, let me show you. See, the derivative of your func with respect to x2 is negative sine x2. And it's a partial derivative. So if you do it in this way, this is the way to do partial derivative. Okay? So, first of all, in the first part of the coding, we need to figure out which way we want to plug in. The second thing that we need to worry about is which way to do derivative. One way is to do diff. Diff means differentiate, which is derivative. But if you really want to use some other tricks right here, maybe you need to use finite difference. Okay, so let's work on diff first. So if I want to use diff, I need to convert this whole thing into symbolic. That's the only way. And for better use later on, I'm going to say fs. S means symbolic. String to sim f. So this is convert to symbolic. Okay? So I convert f into symbolic. So later on I can just say fs. And I will need derivative and second order yes, I need a lot of derivative. So gradient matrix actually looks like diff fs and then x1, right? And then change line, semicolon, diff fs x2 semicolon diff fs x3. We have 4 variables. So diff fs x4. So basically, this is your gradient matrix. Let's see how it looks like. So this is your gradient matrix. You have a gradient matrix and in the form of symbolic. Can you plug in numbers? Yes, you can. Substitute gradient matrix. And what's inside? You need to specify x1, x2, x3, x4, right? And then you need to give 4 numbers. For example, 1, 2, 3, and 4. This is plugging in, right here. Substitute grade. Grade means gradient. And it's in the format of symbolic. This is symbolic, right? And when I plug in, I specify 4 texts, 4 string. I group them in a cell. And each one of them means the name of the variables. And then I give 4 numbers right here. Those are the values I want to plug in. Okay? So this is how you can substitute numbers into a vector and get gradient values. What's next? You need Hessian, right? So your Hessian could be it's a lot of them. So let's find a better way to do it. Because Hessian has 16 terms, I don't want to type in a lot of them because that's a lot of typing. Let me see. I'm going to rename. I'm going to rename this in certain way. I'm gonna say dfx. So dfx means partial derivative of fs with respect to x1. And then, no, I need to say maybe df1. And I have df2, df3, and df4. Okay? Because later on, I need a lot of them. So I'm gonna copy those to here. Okay? I just rename whatever I wrote right here, and then I just need to, actually, you know what? I can put a bracket here. Actually, I can just say grade 1. Can I? Let me see. Yes, I can. Just grade 1. Grade 2. So maybe I call it df1. So I can simplify a lot of things. df2. Okay, and then this is df3, bracket 3, and df bracket 4. Okay? And I don't need the following. I don't need this one. But I need to make sure how, if I rewrite in this way, we need to test it. Okay? What does df look like? df now becomes a horizontal vector. Because when you name your, when you specify the index 1, 2, 3, and 4, by default, Matlab considers this as a horizontal matrix. But in fact, a gradient matrix is a vertical matrix. So what you can do is you can specify the position. This is basically 1, 1. and this is 2, 1, and 3, 1, and 4, 1. If you specify the position in the matrix, then, sorry, you need to clear the memory. If you do it like this, you specify where exactly you want your derivative to be placed, then your df vector is a long one. Okay? The reason why I want to define in this way is because later on, when I do second order derivative, it's easier for me, I think. So Hessian, I can specify them one by one. Hessian 1, 1 is diff of df1, right? And with respect to x1. So you apply a partial derivative with respect to x1 again on top of df1, this guy. So that will be your second order derivative, right? And you do the same thing again for 2, 3, and 4. So here 2, 3, and 4. So replace them by 2, 3, and 4. Okay, so this will be your first row of Hessian matrix. Sorry. Okay, please. Okay, so this is your first row of Hessian matrix. How about the second row? Second row, you only need to specify 2, 2, and 2, 3, and 2, 4. I will tell you why. You don't need to specify 2, 1. Later on, we will handle 2, 1. So for the 2, 2, you basically do derivative against df2, but this one is with respect to x2. Okay? And here you are doing it with respect to x3, and here with respect to x4. Okay? Next, 3, 3, and 3, 4. So over here, change to df3, df3 right here. Last one, 4, 4. Okay? So these are the ones that you need to compute. And how about the other half? The other triangle. So you didn't specify 2, 1. You didn't specify 3, 1. And 4, 1. Actually, 3, 2. 4, 1. 4, 2. And 4, 3. You didn't specify them. They are actually the same as 1 and 2. This is a symmetric matrix. That's why you could you don't need to compute them. So here 3 and 2, 1 and 3, 2 and 3, 1 and 4, 2 and 4, 3 and 4. Okay? So now you have your entire Hessian matrix. Let's test it. So your Hessian matrix looks like this. That's your Hessian matrix. Okay? So later on, when you do inverse, it's easier. Just type in h to the power of negative 1. That's Hessian inverse. You can now do Hessian inverse very quickly. Okay? Even when you change a function, if you say plus sine x1, for example, I just randomly change your function, and you check the Hessian again. Your Hessian has sine, and what's the inverse? You have something sine cosine in your Hessian inverse, and you can quickly plug in, substitute Hessian inverse, and plug in here. I already show you how to plug in here. You can plug in. You can quickly get values in there. And if you want numbers, just say evaluate. Then they become numbers. EVAL will convert these kind of mathematical form into numbers. Okay? So now you have your symbolic formulation for gradient and Hessian. Gradient and Hessian. But sometimes when you write the code, it's quite long. You don't want your code to be too long. Okay, so how can you, let's save this as a main function. So let me call main func. Oh, I already have it. Let's call main func1. Okay. So you don't want your code to be long. You want your code to be compact. So what you can do right now is to shorten your code. So usually what I do is I will open a new string. And over here is for me to shorten it. I want to move some part of my code to the subcode. Okay? So right here I will call this a function. I'm programming a function. And here I will I want this to be my initialization. Initialization. It's too long. Maybe initial. Okay? And you can go back and see what you can shorten. Maybe you can shorten these part. These part are like the part that you could always it's the same all the time. So you can cut everything here and place it right here. So look at this part and see what are the inputs for those and see what are the outputs for those. So the input here, you need a F. Okay, you need a F. You need F. You only need F. DF is generated here. Hessian is generated here. So just throw in your F. And what should be the output? You should deliver your DF and H. Okay. So if you type a function like this, then if you throw in a F, it will generate DF and H. Okay, so let's test it. Okay, let's save it. So a sub function called initial. So you can copy the first line here. Okay, I don't want to lose track. And come here and say this. So if you run the code, you don't need this part. I'm going to make the middle part into comments. Okay, you don't need these parts. So if you run this code, what's happening is you will have your Hessian matrix and your DF. So how do I know I did it correctly? You can move on to a debugging mode, you can make a click right here. There, did you see a minus sign next to your number? Just click on that minus sign and run your code again. Run it. So when the Matlab code run up to this line, because you turn on the debugging, this is like a breaking point. Your code will stop right there and tell you what's going on. And at this point, you can actually move step by step. And usually I will recommend you just to use this one. Run the next line. So if you make one click, it will move to the next line, and whatever you just took the break, that line will be executed. So did you see when I make the click, my workspace has this definition of X, because that line has been executed. So now I make a click again, K has been registered. So if I do it again right here, F is being registered. So now I need to make sure if I'm programming this correctly, your breaking point is at this line, not yet executing. Because this is a sub-function you program, you can actually jump into that sub-function and see what's going on. So this time, if you want to jump in, you need to say step in. So say step in. So once you step in, did you realize your workspace changed? Because you, in this sub-program, you only bring F into your sub-function. You didn't bring anything else. So inside this subdomain, you only have F in your workspace. So this is like a private working space. And then you are now at the first line in this private working space. And then you can continue to step up. Okay? Continue to execute line by line. This is the way for you to get gradient and Bayesian. df is our gradient vector, H is our Bayesian matrix. Once I executed the whole thing, basically this subfunction is finished. And then I go back. When I go back, I'm basically not yet finalized this line. I need to take one more step. So with that one more step, this subfunction just return what was the output inside the subdomain. And the output was df and h. So that's why this dh and f was generated in my workspace at the outside, in the public working space. Okay, so I always think debugging mode can help you to understand what's going on in the for your code. Okay, so I can continue and stop. Okay, so this is a way for you to initiate the code, and also helping you to learn how you can create a subcode. Now, once I know how to formulate df and h, I could start my optimization. In order to create a optimization loop, I need to have a while loop. So while my termination criteria satisfy, while my termination criteria is not satisfied, I need to continue to do my iteration. So I need to define my termination criteria. Usually I define a number called error, and I give a large number. Okay? So while error is larger than 10 to the power of -3, I need to do what's inside my while loop. So this is the usual way for me to program my iteration process. Okay? So when you get in, what's next? You need to calculate your next variable. So now I will say x k plus 1, comma, and then, how do you say this? The two dots. What's the name of it? This. What's the English for Mao? How? Two dots. What do you call it? Nobody knows. Okay, the two dots. Okay, we're poor in English. Okay, so basically, what does the two dots mean? So if you have a vector like this, when you say x1, comma, and these two dots, this means the first row, right? First row, the first row, and then this means everything. This means everything. So first row, every column. This means every column. Okay? And if you say 1 and end means the last one. Okay? And what else? If you say 2 to 3, the second one to the third one. Or you can say second one to the last one. You need to know about the syntax of Matlab. Okay? So anyway, over here, I'm just saying I am increasing the dimension of x. I'm moving on to the next row of x. Right now my k equals to 1. So if I say k plus 1, that means I'm moving on to the second row. So in the second row and every column of x equals to what? Equals to the original one. This is my original one. Minus, what I need is Hessian inverse times gradient matrix, gradient vector, right? But I cannot just do that. I need to plug in my numbers. So how do I plug in? Substitute this guy and use what I told you. x1, x2, x3, x4 in a large bracket and give the numbers. So what are the numbers? The numbers are the current variables. These are the current variables. This is how you plug in. This is how you plug in into inverse. Oh, sorry, this needs a minus right here. How you plug in inverse Hessian. Okay? If I continue to type right here, my line will be too long. There is a way to change your description into the second line without breaking it. Is to use ... Did you see ... The combination of ... converted to a blue color? So ... means change line. Otherwise, my code will be super long. It's very difficult for reading. Okay? So why do I do that? Because sometimes it will be a good way for you to, align certain things in a nice way. So it's easier for you to debug. And then if you put a space right here, it's okay for Matlab. Space for certain positions, that's fine. Okay? So this is one line for Newton's method already. So what's next? I need to evaluate, am I converged yet? So I say error means norm, the current design, minus the previous design. So what is norm? Norm is a function that calculates the length of a vector. So if you use k plus 1 minus xk, that's an error vector, and you compute the length of it. Okay, so you're done, and you need to advance your iteration number by 1. So k equals to k plus 1. Okay, that's it. At the end, you will get optimal solution. Let's see. Oh, something's wrong. Subs. Forget the s. Okay. Oh, what's wrong? Oh, so there's some issues with my vectors. Why? Sorry. Here is what's going on? Okay. Here's a good chance for us to see what happened. I don't know what happened. I make a break right here. I run the code again, and usually what's the error message was something about dimension. So let's see if we can evaluate this guy. Yes, we can. How about this guy? Yes, we can. But can we do multiply? Because what we get is a vertical vector, but this one is a horizontal vector. We define our variable into a horizontal vector. So you need to transpose this guy. So at the end, you will have a vertical variable. But it's not good for us because we initially defined everything into a horizontal vector. But in math, our vector should be vertical. So what should we do? We can change everything into vertical. So let me put one dot right here. That means transpose. Okay, this is transpose. So this means transpose. Right here. So now x is a vertical one. So since this is a vertical one, I need to say everything in a different way. I should say every row and the k plus 1 column, right? And over here I should say I need to change it because I just transpose it. So this is every row and the kth column. Okay? Otherwise something will be wrong. So if you are familiar with debugging, you should be able to figure out where the problem is. Okay? Now let's run again. Something was wrong again. Because here, the way I tell Matlab about my x1, x2, and x3, they are placed horizontally. I need to place them vertically because now these are vertical vectors. So I need to put semicolon here. I hope this is the mistake. Okay, so at the end, when you see this larger than, that means completed. So if the code successfully completed, that means we finished the loop. That definitely means we satisfy the termination criteria, right? But how are you sure if we satisfy the result? You need to display your result on the command window so you can visualize what's going on. So now you can start to display some results on your command window. What you can do right now is, so initially you can say display. So here, to display results in command window. You can say display. So whatever you wrote inside this display has to be a string, and whatever string will be displayed in your command window. So I'm gonna use to demo. If I say display and then the bracket for string, I put a string there. If I do that, in the end, Matlab will just display that string that's inside. But if I want to display a long string with some values in there, you need to combine what you want to say and the values together. So if I want to combine 1, 2, 3 and a value of 2, they cannot be combined together because they are two different kinds of things. The way to combine them is, first, you convert your value into a string. So here, number to string. So if you say number to string, you convert number 2 into a string of 2. But how do you put different portion of strings together? You can use a large bracket, medium bracket. Put them in this way, you can put them together. So at the end, you have 1, 2, 3, and 2. And then this whole thing can be placed inside display. If you say display, this whole thing, then you have 1, 2, 3, and 2. Okay? So this is what I'm going to do. I'm gonna say initial stage, and I'm gonna display my variables. I'm gonna say x equals to medium bracket, and I'm gonna display my current value. So my current value will be a vector, a vertical vector. So I will transpose it into horizontal and then convert into string. So number to string and my current x, but transpose it, because convert vertical back to horizontal. And then close the bracket. Let's see what happened. This whole thing is a bunch of strings. I didn't put them together by another medium bracket. Okay, run it again. So the window will say initial x equals to 0, 5, 5, 4, just like what I provide to the code at the beginning. Okay, so good. And maybe I also would like to see what's the function value for now. So function value, I can continue to lengthen my display. I can say f equals to, so in order to know what f is, you need to plug in. You need to plug in your current variable into your function. So f equals to what? Equals to plugging in. So substitute and f and everything you need right here. Because you already wrote how to plug in, right? And over here, everything is in vertical. That's fine. Here, x is fine. Yeah. And sometimes when you lengthen your code, everything becomes so messy. One good way to make it clear is to make good use of ... So you know what was written inside each portion of the code. So I have a part of the string. I converted x into another string, and then I plug it in. But when I plug in, I need to convert it into a string. So I need to say number to string. right here. So those are the each portion of my long string. So let me show you what will happen. Okay, some mistake. Number to strings. Oh, I didn't convert this into symbolic. So string to symbolic. Because I did it in the subcode. I did it right here, but I didn't do it here. So let's run again. Oh, what happened? Input to number to string must be numeric. Numeric. That's the. Sorry. Let's try something here. So playing with the bad thing about symbolic is that symbolic is not number. Symbolic is symbolic, even though it looks like a number, but it's symbolic. So you need to evaluate it. Because EVAL converts everything into numbers. So when this is a group of codes. First, F was a string. I converted it into symbolic. For symbolic, you can do substitution. You can subs. But when you complete a substitution, even though your result looks like number, but the result in fact was in the format of symbolic. To convert symbolic into numbers, you need to say evaluate. Okay, you need to do that. So over here, I need to say evaluate. So this is a very long line. Okay, I'm sorry. Let me repeat again. A function, which is string, converted to symbolic, so you can substitute. Now you replace x1, x2, x3, and x4 by the current variable x. But at the end, the result is still symbolic. You use evaluate to convert it into number, and then use number to string to convert it into string. It's a very long process. But once you complete the line, it's done like that in a very short period of time. You get the function value. Okay? And I also, I think that's okay. So initially, my function value is 4a3. Okay? Then I'm gonna display some results during my iteration as well. So maybe I could display whenever I computed the error, or at the end. Let me just display the result at the end, right here. So I just copy what I wrote right here to the bottom. Let's copy the whole thing. Okay? But during the iteration, it's no longer the initial states. It's actually in certain number of iterations. So I'm gonna say iteration with a number. Here. Here I need to put the iteration number. What is my iteration number? Basically, k is my iteration number. But in my code, I already I already plus 1. So maybe I should do the k plus 1 later on. Let me do the k plus 1 afterward, after the display. So here, number to string and k. I convert the number k into a string. Okay, and of course, dot, dot, dot. And what would be my x? My x will be my new design right here. So I'm gonna display the new design right here, but of course I already transpose it. And then I will plug in my new design into my function. So when I plug in, I will be doing it right here. Am I plugging in vertically? Yes. So let's see what it looks like. So actually, it took several iterations to converge. I don't know why. Usually because it's Newton's method. How come it's taking some time? Anyway, we'll figure out later on. Because it's a quadratic function. Supposedly you should, I put a sine function right here. That's why it doesn't converge in 2 iterations. Because sine function is not polynomial. That's why. Okay, if I get rid of the sine function, converge in 2 iterations. Okay? So maybe we can keep the sign so we can see more iterations. And maybe we also would like to see what would be the value of your error. So over here, you can add more to display. You can say you want to say what? A space, comma, error. Oh no, do I do a space? I do a comma first, space, error equals to. Okay. So here I will display the current error. So current error, number to string error. And display. So here you can see the error was 17 and then reduced to 0.9, 0.14, 0.002, and then a very small number, power to the -7. So it converged. If you want even greater accuracy, you can make this small number even smaller, maybe to the power of 10. Very, very accurate. So one more iteration, you reach to an accuracy of power to the -14. What if I want to have even greater accuracy, 20? I don't know how many iterations. 7 iteration, error is 0. Cannot be even more accurate, 0. Okay. So if you are looking for, but in fact, you don't see a difference because you only display 4 digits in your X1. Okay, and actually there are like a tiny difference. But for engineers, we don't need that kind of accuracy. -3 was already good. Okay, so 5 iterations. Okay, so this is Newton's method. And maybe you would like to change this whole thing into a general code, and then you want to switch methods. So let me show you how you can switch to steepest descent. So let me open a subcode and say function. Here I will say new, and then say Newton, and say old. How about that? So here basically I want to replace this line by I want to be able to switch actually if I run steepest descent, that requires me to do line search. That's a lot of coding. Anyway, but maybe some other time. Okay. Maybe I show you maybe I show you without subcodes. Okay, this is Newton's method. So, Newton's method. So if I do not use Newton's method, what can you do? I directly program in the same function. If I try steepest descent. So here I will copy this whole thing here. But this part I will make it into a comment. So for steepest descent, you don't need Hasium. So you need a new variable called alpha. Okay, you need alpha. But you don't know about alpha. So alpha needs to be an unknown variable. So I can say symbolic alpha right here. Okay. So let's see what will happen if I do that. Why? Sims. No. Why? Sim. Let me see what's going on. The output is symbolic. I'm debugging. Too many output arguments. Oh, how about this? If I evaluate the whole thing. Ooh. How come I cannot do multiplication? Oh, how about I try this? Alpha and then dot multiply. No. Sim alpha. Sims alpha. Sims. So stupid. Converting sim to double. So the following error, unable to convert expression into double array. So maybe I need to say evaluate. Okay, when you do programming, that happens. Let me stop here. Why can you do this? Yes, you can. Because X is double, whatever that's behind it is symbolic. So how come they don't put and your x is numeric. You cannot, so the output right here is symbolic. You cannot assign symbolic into double because your x is double. So right here, I will just say temporary variables. Okay, let me say temp. So what is my temp? Temp is my variable without knowing alpha. This is what you wanted to do for line search, right? You plug in, but you don't know alpha. Then you need to do a you need to plug back to f. So your f with alpha, after you plug in temp back to your f, you will get a function f in terms of alpha. So f alpha equals to substitute f and then basically substituting. Okay, substitute everything. But when you substitute temp. Because temp is the variable where x is your new variable. Temp is your new variable in terms of alpha, right? And it's in the vertical vector. So it's okay to substitute in this way. Okay, and of course, convert string to symbolic. So what does f alpha look like? F alpha is a bunch of alpha. Everything is being written in alpha. Okay? This is your f alpha. So now I have a function in terms of alpha. I can do Newton's method to do line search. So I can say I need a derivative of alpha, df of alpha. So df alpha is diff f alpha. And what I can do is my variable is alpha, and then I can use initial guess by 0. And my ddf is my second order derivative. Will be another derivative, but this time you apply on top of df. Hold on. You need to plug in at the last. So sorry, this is only derivative. This is only derivative. And here you have d. So df is first derivative with respect to your f. ddf is a derivative to your df. Okay, so let's see what happened. So df alpha. df alpha. Let's see what it looks like. df alpha is this. ddf alpha is this. Okay, so now I can, but I need to plug in alpha. I will plug in right here. So substitute, and then alpha, and my initial guess is 0. So directly substitute here, and then alpha and 0. So let's see what in the end, what do you get? Your df alpha is this number. ddf alpha is a different number. 0. 0 is quite strange. Second order derivative, but it's 0. Sorry. I have to substitute later on. Okay. I need to do derivative first, and then I plug in number. So df alpha and plug in number. I put a underline V. V means with value. Is to substitute df alpha and then plug in 0. Okay. And how about the DDF? Here is DDF. Okay. So these are how I plug in. I plug in numbers. So then you can use Newton's method. So your alpha new equals to your initial guess, which is 0, minus your first order derivative over your second order derivative. So this is line search by Newton. And you know it's a quadratic, it's not quadratic function. It's we have sine and cosine. So it actually needs to iterate. It actually needs to iterate. So I'm actually writing, I need to write a sub-iteration loop right here. Okay. So let's do it. Because Newton's method cannot get the solution right away. If this is the case, I will do another while loop, maybe starting from here. So I define an error. This is for the alpha loop error. I start with some number large, and then my initial guess, alpha value, initial guess is 0. Okay, so my while loop is inner while loop. When this error is larger than 10 to the power of -3, I need to do iteration. Okay, so I need an iteration number. So let me use m as my iteration number, starting from 1. So here originally I wrote 0. Now I'm gonna say alpha value bracket m. Alpha value bracket m. So starting from the first one. So here I will have alpha value m plus 1. Right? So this is Newton's method. And then I need to update my error, which is absolute value, the new design, minus the old design, which is bracket m. And here I should have my old design here. Okay. That's fine. Let's see if it works. Run the code. Step. My DF is some number like this. DDF. Oh, I accidentally run the code. And you feel I think it was trapped inside the while loop. Hold on. Step. So DDF is this number. So my alpha V is the second one, 0.0571. Another one, my error is this big. So go back. Oh, my M didn't advance by 1. That's why. Okay, let's see if I can jump out of the loop. Okay, sometimes it happens because I have sine cosine there. If I have sine cosine, it will move back and forth. It doesn't stop. Okay, it doesn't stop. So this loop doesn't stop because sine cosine is not a good function for us for line search. So for this case, I'm getting rid of this. So let's run the code again. Step. So my optimal alpha is 0.0572. Step. Another run. Now my error is 0. My final alpha is 0.0572. So at the end, error alpha. Well, that's why it didn't stop. So maybe it was okay. So let's move the sign back. Thank you. That's why. Oh, yes. So actually it stopped at only two iterations. Okay, nice. So now I have a alpha value. I just need to plug back to my temp. My temp was my new design point. So my new design point actually is temp. So substitute temp and replacing alpha by this new value, the last one. Okay, I hope that works. Okay, so it was able to find a new set of solution, right? And then we can try to see if the whole thing can work. So you will see steepest descent is not a very efficient method, but it actually converged by 41 iterations. Okay, so let's keep in mind this is the solution. Let's copy it. Let me copy the last line, just for us to compare. Okay, so this is steepest descent, and what we got was this. So let's turn it back to Newton. Turn it back to Newton, and let's hide these portions. Okay, and let's run Newton's again. Newton. Okay, this is the solution, and we can now compare. Okay, did we got almost the same results? Yes, we did. Very similar, only several digits tiny difference, and same optimal value. So you just confirm Newton's method and steepest descent eventually finds the same result. But it seems like you need a lot more iterations to get the optimal. Okay. But how about conjugate gradient? Maybe conjugate gradient can do better. Since we already have steepest descent, we can quickly convert this into conjugate gradient. Okay? Conjugate gradient. So in order to do conjugate gradient, in the first iteration, you are basically doing steepest descent. But in the second iteration, you update your moving direction. So in the first iteration is the same. So we can keep steepest descent for one iteration. So the easiest way to do this maybe is to move the whole thing to a subproblem. Okay, let's move the whole. Let me show you how to move it. Create a new script, and you can cut the whole thing, cut it, and then paste it here. Because this is basically what you did for steepest descent. Okay. Again, you say function, but you need to figure out what was the output. So the output was your x. What else did you output? You didn't output anything. Just deliver out x at the end. Okay, and you name this function as steepest. Okay, so what was the input? You need this guy. You need x. So x is your input and also output. And for x, you need your index number, iteration number k. You need df. You need df here. You need f. What else do you need? No, you don't need anything else. Everything will be, the rest of the things will be computed within those. So in order for this portion of code to run, you need to provide those. And then you deliver x, you update x. So you just copy this whole thing back to your code here. Okay? And save it. I already have a code called Steepest. So let me rename this Steepest 1. Okay? Steepest 1. So here I should call Steepest 1. So just make sure there's nothing wrong with it. Just run it again. Okay, there's something wrong. What happened? Unable to create user because alpha is okay. So don't call it, if you are in the main code, you can use some of the names that's existing in Matlab. But when you are calling subcodes, Matlab will be confused whether your alpha is a variable or a function. So don't name it alpha. You can name it as alpha underline. So rename those by alpha underline. Whenever you have an alpha, rename as alpha underline. Alpha underline. I think that's only where I have it. Is it? Run again. So no, something was wrong. Okay. Line 15. Oh, it was named alpha underline, sorry. Also, everything here should be alpha underline. Because that was the new name. Okay, so I just moved a chunk of code to a subcode, and it gets the same result. 41 iteration. Now for conjugate gradient, I can run this for one time. That save me a lot of time to rewrite a portion of Steepest descent. Okay, so for conjugate gradient, I need this. Okay, but I don't need the Steepest descent code anymore. I will highlight it. So for conjugate gradient, in the first iteration, I do this. So I will say if my iteration number k equals to 1, then I do this. Else, I need to do conjugate gradient. Okay. So how do you do conjugate gradient? You need to of course you need something similar right here. You need to actually you need almost the same thing. Copy it here. I just copied my conjugate gradient here, but this time I will need to. It's no longer df. It's a moving direction, and here is plus sign. So how do you evaluate your moving direction? So dir is the key, moving direction. So your moving direction should be negative gradient plus a chunk of stuff. You know what? I think I better rewrite the whole thing for conjugate gradient, just for more precise definition. So first I change this negative sign to positive, and then I'm gonna define my moving direction. So dir should be negative gradient, negative df. Let me see if that works. Okay, so my moving direction is this guy, but it's negative gradient. So here plus, I should say dir. Okay, do I have df anymore? Okay, so if I keep on doing this, actually this is steepest descent. Yes, if I didn't update my dir, this is steepest descent. I'm keep on moving along negative gradient. But starting from the second iteration, my dir needs to be updated. So if k equals to 1, then my dir could be this. Otherwise, my dir is different. So my dir will be my previous dir. Is it? No, my dir should be negative gradient plus something times my previous dir. And since in the starting from the second iteration, whatever I had in dir was my previous dir. So it's okay to write in this way, right? I just need to write down what's in front of it. I don't remember it. Then I need to check my notes very quickly. Almost done. We are almost done here. So the current gradient dot product with current gradient over previous state gradient dot previous gradient. So where did we compute gradient? Basically, df is our gradient. So in the second iteration, df, this is my current iteration. df is current gradient. So here, how do you do dot product? So one thing over the other thing, right? One thing over the other thing. This is first gradient dot product with first gradient. So df transpose times df. df is a vertical vector. If I make it a horizontal one times itself, the vertical one, then that's dot product. Now, over here, I need to compute the previous one. So for the previous one, that's an issue because we don't have it. We need to substitute. In fact, I think I better compute df first. I think that would be a best way. Otherwise, I can make mistakes easily. Current one and previous one. So whenever I compute it, this is the previous gradient. Okay, so maybe I memorize it. I call this previous gradient. I memorize it. So in the first iteration, I just memorize it. This is the previous gradient. Okay? And so when I need it, I can. No, I need to plug in. Then I need to plug in. So it's the previous gradient. So this portion actually is where I computed the gradient. So maybe I would moving direction, that's fine. Okay, so let's just compute previous gradient and current gradient. I think we better do it. Okay, so what would be the previous one? So gradient is df, and you just substitute in the current design and the previous design. So current one, this is your current design. -1 is your previous design. Okay, so current gradient, dot product with your current gradient, and then previous gradient transpose times your previous gradient. That would be your too long, dot dot dot. So your current gradient dot product with your current gradient over previous gradient dot product with your previous gradient to update your moving direction. Here is dir is your previous direction, and df is actually the current gradient. Okay, try it. Not a number. Something's wrong. Why is that? But I think it found the solution somewhere close. Yeah, it found the solution, but I don't know why not a number right there. So maybe some of my calculation. Oh, because I did the previous gradient was 0, is it? But it's not converged yet. So let's see what's going on. In the 20th iteration, something was wrong. So we just need to run the code 20 times. So in this one, something will be wrong. Previous gradient, current gradient. Let's see. Direction. Okay, we're not sure if that's okay. Okay, temp. Okay, not a number. So what makes this whole thing become not a number? dir is long. Let's see what's dir. dir right now is very long. Let's evaluate dir, see what's going on. Oh, there's x1 in there. How about temp? Was temp not a number? Temp was not a number. So let's see, what is this one okay? Oh, the result of this makes it not a number. How about substituting? Substituting is okay, but to evaluate it, we get not a number at the end. So let's try I don't know why. Oh, cosine. We have a cosine here. So when does let me try something easier. Let's try to avoid sine cosine. Maybe it's better for us. Did I? Let me try some other methods. So if I use conjugate gradient to solve this problem without sine cosine, also 41 iteration. If I try Newton's method, should be 2 iterations, but how come steepest descent is making a mistake? Previous current negative df dir. Oh, dir is I need to substituting dir. So I better memorize it. I better memorize it, otherwise I can make a mistake. Previous dir equals to dir. So every time I evaluate, no, this is not the way, because I haven't substitute. So just substitute dir right here. Just substitute it. But here I need to use -1, the previous one. I think this should be it. Okay, 4 iteration. See? So this I actually enjoy debugging, but maybe you are not. Let me show you the difference. Let's work on Newton. Oh, actually, we can do the sine problem again. Plus sine x1. We can do it. Okay, this is a sine problem, 5 iterations. Okay, hide this, and let's unhide conjugate gradient. Okay, so for steepest descent 41, Newton 5. How about conjugate gradient? 9 iterations. And did we get the same result? We can copy it. Okay. So 10.3145, 10.315, 7.4949, negative 0.3, negative 0.3, 0, 0. Okay, same function value. Right, so from here you can tell conjugate gradient is quite powerful but easily incorrectly written code. You need some time to debug. Okay, and here is the confusing part. Okay, for the update formulation, you need to substitute in you need a current gradient, previous gradient, and you also need a previous direction. Did I use previous direction? Oh, this is my previous direction. I directly plug in. Is it correct? Just double check. I think I did it right, but I feel like I question myself. So if I step in, dir looks like this. So this is your moving direction in terms of x, y, x, all your x. And you continue to a new iteration. So this is still your dir. And then you substitute in with your old variables. And then if you move on, step, your dir was updated. Okay, so correct. So that's a confusing part. Okay, I know if it's very confusing, but you need to have a very clear logic about what's going on. Okay, so I'm giving you the entire code. You can have it. Okay, and if you really want to being able to code like this, it needs a lot of practice and also very clear logic. Sometimes you see error message. It's okay, just like what I show you. I could make mistakes as well, but you need to understand what does the message mean, and with more experiences, you will know what mistake you may be making, and you can quickly revise it. Okay? So that's it for today. I will send you this very long, boring video. But if you would like to understand what was going on, then you can watch the video.